Another day, another learning. Once again, I am Richmond S. Marstella from BSED Math 3B. For today, I will discuss about the cyclic subgroups. So for here, we will identify which are the cyclic subgroups. So on our past discussions, we showed our different subgroups. So we have Z13 and then Z1 to Z14 and so on. So for our improper subgroup, so to identify if our subgroup is a cyclic, we need to determine our our generator. Okay, the generator of our elements or the subgroup. Okay, so here it must be abelian, and the subgroup must have at least one element or one generator, which means when we say generator, an element that generates all the elements of the set. Okay, so let's start for our C13. So we have P. So P star P is equal to P. So we're going to stop. Then C star C is equal to BA. And then BA star C is equal to L. And then L star C is equal to MO. And then MO star C is equal to N. And then N star C is equal to BU. And BU star C is equal to MA. And then MA star C is equal to P. So we're going to proceed to the next element. BA star BA is equal to MO. So MO star BA is equal to BU. Then BU star BA is equal to P. Going to stop. Next. So we're going to continue this for our remaining elements. So here, as you can see, there is no at least one generator with 16 elements that generates the 16 elements. So therefore, it is not considered a cyclic subgroup since no single element can generate the whole group. Okay, next one for let's proceed to our Z sub 1. So P, then MO. So here P star P is P and then MO star P is MO and MO star MO is equal to P. Okay, so you can see here, we have a generator for in our elements MO, we have MO and P, which generates the whole group. So therefore, it is considered as a cyclic subgroup since there is a single element that can generate the whole group. Next one, for Z sub 2, we have P and P2 under binary operation star. So P star P is P, and then P2 star P is P2, and then P2 star P2 is equal to P. So therefore, it's considered a cyclic subgroup since there is single element that can generate the whole group. So next one, for our Z sub 3, we have P and MA2 under binary operation star. So P star P is P and MA2 star P is MA2, then MA2 star MA2 is P. So therefore, it's considered cyclic subgroup because we have a generator MA2. Next one, C sub 4, we have P and PU2 under binary operation star. So P star P is P and BU2 star P is BU2 and BU2 star BU2 is P. So we have a Pu2 or the generator Pu2. That's why it's a cyclic subgroup. So next one, for our Z5, we have P and N2. So for our P star P, we have P, and then N2 star P is N2, and N2 star N2 is equal to P. So we have a generator N2. That's why it's a cyclic subgroup. So next one, Z sub 6, we have P and MO2 under binary operation star. So P star P is equal to P, and MO2 star P is MO2, and MO2 star MO2 is P. So therefore, it's a cyclic subgroup because we have a generator MO2 that generates the whole group. For C sub 7 is equal to P and L2 under binary operation star. So P star P is equal to P. L2 star P is L2, and L2 star L2 is P. So therefore, it's a cyclic subgroup because we have L2 that generates the whole group. For Z sub 8, it is equal to P and BA2 under binary operation star. So P star P is P, and BA2 star P is BA2, then BA2 star BA2 is P. So therefore, it's a cyclic subgroup. And for C sub 9, we have P and C22 under binary operation star. So P star P is equal to P. C22 is star C22, so it's equal to P. So therefore, it's a cyclic subgroup because we have C22 or the element C22, which generates the whole group. And then for Z sub 10, we have P, C, PA, L, MO, and PU, and MV. So P star P is P, C star C is BA, BA star C is L star C is MO, MO star C is N star C is BU, BU star C is MA, and MA star C is equal to P. Then BA star BA, MO, MO star BA, BU, and BU star BA is equal to P. Next, L. So L star L, BU star L is equal to C. Then C star L, MO, MO star L, MA, MA star L, BA, and BA star L is N, and N star L is P. So as you can see here, we have two generator or two elements that generates the whole group, or four rather, four elements that generates the whole group. So therefore, it's a cyclic subgroup. So it is considered a cyclic subgroup. So next one, we have P, MO, P2, MO2. So for P star P is P, MO star MO is P. So next one, P2. So P2 star P2 is P. So next one, MO2 star MO2 is P. So there is no single elements that generates the whole group. Therefore, we can conclude that it's not a cyclic subgroup. And then for C sub 14, we have PPA, MO, PU. So for P, We have P star P is P, BA star BA is MO, MO star BA is BU, and BU star BA is P. Then, as you can see, we generates or there is an element that generates the whole group. Therefore, we can conclude that it's a cyclic subgroup. And of course, for our trivial subgroup, so we have P under binary operation star. So P star P is P. So it's a cyclic subgroup because it generates the whole group. So therefore, we can conclude that Z11 and Z13 are the subgroups that are not cyclic. And then the rest of them, they are all cyclic. So here, relation between the order of a group and the order of its subgroup. So the number of elements in the group Z is 16. So our elements is 16. And then the numbers that can evenly divide 16 are 1, 2, 4, 8, and 16. So we call them our divisor or divisor. So it shows that a group can have subgroups whose number of elements is one of these divisors. So as we can see or as we observe on the table, we have a trivial subgroup. It has one element, which is the P, and our improper subgroup, which is which consists of 16 elements. And then for our proper subgroups, for Z1 and then from to Z11 and Z14, we have an element 2, 4, and 8. So we can conclude that the order or size of any subgroup must be a divisor of the order of the whole group. It means we cannot find a subgroup that is not divisor or that is not divisible by the group. For example, our group or the our elements is 12. So the elements or the number of elements of our subgroups must be only 1, 2, 3, 6, 12.